Okay, well, good morning, all. Good afternoon, good evening, depending on where you happen to be joining us from. Welcome to the second in a series of Creo Simulation Solutions webinars. We had one a few weeks back delivered by Sevi Beaver, a coworker of mine, on Creo Simulation Live. So hopefully some of you got to witness that. If you did not, we do have a recording of it. And then we'll be following this webinar up with another webinar that will be on the Creo ANSYS simulation solutions. Now, notice I said Creo ANSYS, not just ANSYS. So it's the ANSYS product that is built within Creo. Hope everybody is excited and ready to watch the presentation here. I promise not to bore you too much. A little bit about myself. My name's Terry Robbins. I'm the manager of Star Support within PDSVISION. I have been using Creo PTC software since its inception in the late 1980s in the automotive and defense industry, primarily using RASNA/Mechanica/Simulate as the PTC analysis tool. Excuse me. And then all of the Creo functionalities for product development as well. Please feel free to enter any questions that you have into the chat. And when I finish, I will try to answer those. If I can't answer them readily today, I will research those and get back to you as I will know who they came from. So I'm going to do a little bit of a demonstration at the end. Not a whole lot, but I'll show you a few things as to what we can do with the software. Primarily, I want to wet everybody's whistle about what you can do with Creo Simulate and why we would want to do this. So we're going to talk a little bit about the product introduction. We're going to talk about what its capabilities are, and we'll talk about the opportunities and value that it brings to your engineering organization. So what is simulation? From a Creo standpoint? Well, Creo Simulation is an analysis tool that does structure, thermal, and vibrational analysis solutions on models. It analyzes the digital 3D data, so you don't have to build prototypes as often. You don't have to worry about wasting the material, reusing the material. This is all built off of CAD models. It can use any CAD model that Creo can bring in, so we can bring in step files, SolidWorks files, but it's also integrated within the Creo parametric software package itself. So this allows you to build virtual prototypes from the models that you actually have developed within your CAD system. So what types of analysis can we do with simulation? Well, we have basically structure, thermal, and then we have some advanced functionalities that we'll talk about in a little bit. And I'm going to hit briefly on each one of these. So in case you're not familiar with them, we can tell you about what they do. So first off, we're talking about static structural here in the upper left. You can just basically do linear structural analysis, small displacements, objects moving just a very little bit because they have a pressure or something on them. We can also do pre-stress analysis. An example of a pre-stress analysis would be either adding or removing stiffness from the object you're trying to analyze. Best example I can give for a pre-stress analysis is if you're familiar with pre-stressed concrete, they stiffen the concrete by putting rebar inside the concrete, stretching the rebar a specific amount, letting the concrete set, removing that tension that they have on it so that it compresses back, and in turn it stiffens the concrete. We can do large displacement analysis. This is where you have external loads that cause the object to get deformed more than a slight bit. So let's say you've got a diving board. The diving board is going to flex for many inches, if not a foot or two at the end of it, as you're bouncing on it to get into the water. That deflection is a larger amount than the diving board is thick. So it would be a large displacement over a small area. So that would be considered a large displacement analysis. We can do contact analysis. We can analyze where two objects would touch one another. So imagine you have a circuit breaker or a switch, and you flip that switch. The contact is going to actually touch the other end. We can determine the contact area, the contact pressure, and we can also apply slippage to that so that you can have your friction coefficients in there. We can do linear buckling. This is a stability analysis where you can actually take a column or something resembling a column and basically press on it along the parallel line of the axis. And at some point in time, you will provide enough force to that object until it will buckle. So it will predict the location or the forces that it would take to buckle the column. I must emphasize here, any behavior or analysis numbers that you see after the object has buckled are not considered to be valid. It does not do post-buckling behavior. It will give you some results, but they are not validated or verified. It's just what happens after the object buckles. Finally, we have our stability analysis that's nonlinear, and this is called a snap-through analysis, and that's all based on large deformation of your object. So maybe you've got a disc that's got some fins or some fingers on it. You can actually go in and do a stability analysis based on your large deformation. So all of those are static analysis types. The next type that we have from structure is our dynamic type. Dynamic meaning motion. First one that you see here is a modal analysis. We can do a modal analysis to determine the natural frequency of an object, whether it be a part or it be a subassembly. Why would a modal analysis be important? Well, let's say you're designing a component or a sensor that's going to go onto an engine block or it's going to go onto an airplane. When those objects are in use, they vibrate. The engine will vibrate, the airplane will vibrate. You would not want the vibration of that to be the natural frequency of the sensor or component that you're adding, because it would then basically cause that particular component, be it a part or an assembly, to fail. We can also do pre-stress analysis with modal. That typically is done primarily with the example that I can give you would be a pre-stress analysis on objects that would have frequencies that would cause the objects to fail. In essence, an earthquake in California. You would want to do a pre-stress modal analysis knowing that, okay, I know what the natural frequency is. What happens to my stiffness as I'm adding components and braces and the like to it. The four dynamic types of analysis that we can do are dynamic frequency, dynamic time, power spectral density tables, and then we can do dynamic shock. Now you notice in the dynamic shock analysis at the bottom, it says earthquake analysis. I will change that a little bit and say that is a seismic analysis. We're talking about two objects and the forces that are moving against one another. It says earthquake because that's the way an earthquake happens. The plates move with respect to one another and they cause the quaking effect. Imagine, if you will, yanking a tablecloth out from under dishes. That would be a dynamic shock analysis because it's seismic. You are basically jerking, yanking, or pulling the tablecloth out from and under the dishes. So that would be your dynamic shock. Then we can have dynamic frequency. So what happens is your frequency increases. What happens is the time increases and the like. Finally, we have a thermal analysis. We have two types of thermal analysis that are out there. You have steady state thermal analysis, which is going to enable you to just see the heat transfer, the heat moving through an object as something is heated up. And then we have a transient thermal analysis. A transient thermal analysis is one in which you have a time factor involved within your analysis equation. Within the thermal analysis, we can do conduction, convection, and then the third type of thermal analysis is radiation. Radiation, we kind of have to simulate, no pun intended. to get to it because we don't do true radiation simulation. Radiation simulation is the transfer of the heat via electromagnetic waves. Conduction is, as you would suspect, two pieces touching one another and the heat being conducted from one to the other, i.e. the stove touching the bottom of a pan. And then finally, we have convection. And there's actually two types of convection heating that we have. One of them is called natural. And I think we've all probably seen it on a hot summer's day. You look out across a blacktop highway and you can see the waves of heat coming up. That is natural convection. You have forced convection. Forced convection would be forcing the water inside of a radiator through the radiator, heating up the cells on the radiator, and then convecting the heat away by mixing it with the air that's coming over the radiator. So those are the three types of thermal transfer of heat that we have within the system. One thing I will mention, the Simulate Thermal enables you to analyze those fields and heat flows. It does not calculate these conditions automatically. Simulate Thermal is not a CFD program. It is not a computational flow dynamics program. We do have a flow analysis program. It is put out by Simerics. It is integrated within Creo, just like Simulate is, but it is not part of the Simulate package. So, but you can do CFD with the flow package, and that will be in one of the upcoming webinars as part of this analysis series of webinars. So why do we use simulation and what's going on out there? Well, this enables us to go out and analyze or test objects in the virtual world. We don't have to worry about building prototypes. We have sustainability. It lets us do multiple different scenarios without having to build an engine block every single time. One of the things that I was involved in years ago in my early career was involved in crashing cars. You'd go to the GM test center or the Ford test center, and they'd actually run a car into a concrete wall when they were coming out with airbags. They don't have to do that anymore. Now, they still do, but they don't have to do near as many of them now as they did before, because you can use these tools to simulate that particular type of a crash or type of condition. It'll allow you to find flaws in your system, and you can process those flaws and get them worked out. It's much easier to have an analysis computer in the software and be able to simulate the crash on 10 vehicles or 10 airplanes as it is to go out and buy 10 cars or 10 trucks or 10 airplanes. So it enables you to do this in a much cheaper, better, faster way. It lets you do this early in the actual process of your design. You don't have to wait until you get one built. You can actually do this all on the actual CAD data itself. Now, we keep talking about the CAD data, and I'm going to tell you why that's important here momentarily. You can eliminate the reliance on prototypes and late stage information. Something changes late in the process in the digital world, make a couple of parameter changes, hit run, you can do it again. Something happens in the late stage of a prototype, you may have to go back and rebuild the entire car, airplane, truck, whatever the device is that you're trying to run the simulation on. I would like to say reduce the reliance on prototypes. I am sure that eventually we will get to the point where we eliminate the need for building actual prototypes. The software will get so sophisticated and dependable that we can do everything based off of the simulation. I don't think we're quite there yet, but it would definitely reduce your reliance on prototypes. It also mitigates your risk of product failure. If it fails in the computer, you make a change, you go on. You don't have to go out and get the other car. You don't have to go get another plane. It lets you validate warranty and reliability as you're moving along and help you to get your product to market faster and built better than if you have to take the time to do full-blown tests without analysis. Mind you, I'm not for one or for the other. It's a combination. It's a marriage of the two that work together hand in hand so we can put out the best product as quickly as possible. So now let's talk a little about I keep talking about the CAD model. With the CAD model that we have, and we're talking Creo parametric here, you design the model. You don't have to take this model out and put it into a different software package. Creo Simulate is part of the Creo parametric family. All you have to do is click a button and it will take you from the Creo parametric model definition seamlessly into your pre-processing. Within your pre-processing, this is where you go in and you specify what your materials, displacement measures, those type of things are. I like to refer to something called the simulation pentagon. Everybody's familiar with the pentagon, five-sided building, but you need 5 things in order to do a simulation. And I don't care if it's Creo Simulate, if it's ANSYS, if it's a SolidWorks product, if it's an NX product, you need a model. We have a model with Creo here. You need to specify a material so that you know how this model is going to behave. Obviously, steel is going to behave differently than aluminum or wood. You need to know how this model is constrained, how's it being held, how's it being used. So all of those things can be done within Creo. That's part of the pre-processing. How are you loading it? Okay? How does the object react when you apply a force to it or a heat to it? And then finally, you specify an analysis. Do I want to see a static analysis? Do I want to know what its natural frequency is? I run a modal analysis. Do I want to see how the heat transfers through there? I'll run a thermal analysis. Is it a column? Do I want to see if it's buckling? I can run a buckling analysis. So that's the final one that you would put in your Pentagon as the type of analysis that you run. So all of that can be done seamlessly within Creo. So we define our model. So let me get my cursor here. We define our model in Creo parametric. With the flip of a button, we are into the actual simulate product where we can define materials, displacement, measurements, forces. So in other words, constraints and loads. Measures are just what you're looking for. There are predefined measures in there: maximum deflection, maximum stress, minimum stress. You can calculate your own measure as to what specifically you're looking for. Materials, and I'll show you when I do the example in a little bit. There's a materials database. If you don't like the material or the material's not in the database, guess what? We can create our own material. And I'll talk about that a little bit when I'm doing the example. We then run the analysis. This is a static analysis, and we can go out, finish it, and we get the results. So here you can see the model has been meshed. It's had loads and constraints applied to it. We run the analysis. Now we get a fringe plot showing where we have areas that are affected. That could be stress, that could be displacement, depending on the type of result that you're asking it to see. Optionally, we have what we call design optimization and design of experiments. You can run what-if scenarios, or you can optimize this. You can say, I want to optimize this part for minimal stress, minimum deflection, maximum deflection. And the system will take your geometry, your loads and constraints, a range of dimensions that you will allow it to vary, and it will optimize the part based on what your goals are. So all of that's done seamlessly and concurrently within your design package of your Creo parametric software. It supports concurrent design. It leverages your data back and forth out there. So the seamless integration lets you cross those barriers where you don't have to worry about converting from a step file or a SolidWorks file or an NX file, any of those other file types. You have one common model that you're working on. So this gives you ease of use. You don't have to have multiple models. Gives you the common data model. So if I optimize this, I have the option to say, propagate this back to my Creo model. It will then update my original Creo model. It makes a copy of your Creo model initially, so you can run a multitude of different scenarios and it not change your original geometry unless you ask it to after you've done the optimization. Again, this is seamless. It is a PTC product. It is not a third-party product that is out there. And the other thing is the results accuracy and reliability. Typically, individuals that are running Creo Simulate are not going to be the full-blown subject matter expert of analysis in the particular field that they're in. Now, they may be. It's not to say they couldn't be, but typically this is being run by engineers at the design level to better design their parts. So the ease of creating this assembly, the process that you go through to set it up and run it, the results that you get back and the accuracy have to be reliable so that you can push these on down the road or on downstream within your design process and be dependent upon the geometry and the results that you get. The other thing that it gives you is with the reliability is the same interface. You have the same interface within Creo Parametric as you do within Creo Simulate. Only difference are your choices. Whereas you may see create a extrusion in Creo Parametric, it may say add a constraint on the menu bar in Creo Simulate. So you don't have a foreign menu. Everything looks the same. Everything is consistent throughout as we're going through the process of putting these objects together. Differentiations, again, we talked about the consistency of the user interface. So you get tabs across the top, you get a menu manager, you get a model tree on the left. When you go into Simulate, it will split. You'll have your regular model tree for your Creo, and then you'll have a simulation model tree, which will show you loads, constraints, meshing, those type things. So you have a consistent user interface. You still have context-sensitive menus. So you hover over it, it will give you a help ticket or a help trick. You have right mouse button access, so it still behaves the same as you're in Creo. You still have your middle mouse buttons, you know, spin, pan, zoom. All of that still works just like it works in Creo. And it uses typical accepted engineering terminology that you have out there. So it uses loads, constraints, von Mises stress, deflection, maximum principal stress, all of those things that you may have learned or have heard about in doing analysis. It doesn't use any specific to PTC Creo Simulate terminology. It uses standard engineering terminology. As a matter of fact, if you design a beam and you specify it in Simulate and you hit the info button, it'll show you a page just like you would see if you were looking at a beam design handbook from CNC or any of the engineering design houses or textbooks that you may have seen possibly in college or on your reference shelf. Differentiations. So we have one model here. We can go through, and this is the Simulate model. We can run several different concurrent designs on this. So we can do one, we can go in and we can change it through design optimization. We can do a design of experiments. Let's say we design a block that's 1 by 1 by 1, and we want to know what would happen if we went 2 by 2 by 2 or 2 by 2 by 1. We don't have to go back and remodel that geometry. We can actually go into the design study and change the value of that particular parameter. It will then reanalyze that model based on those new numbers. It does not update your model, but the design values will reflect the new numbers. And then if those numbers are valid, you could then go in and change your model. It directly reads your material properties in your units. Excuse me. Pardon me. It directly reads your material properties in your units from your model. It's going to apply your loads and constraints to your model geometry. It'll automatically update when your design updates. So if I go in and I have a hole and I make that hole twice as big, then it is going to, I apologize for that, that just popped up. It will automatically update when your design is modified. It also supports sensitivity and optimization studies. Now, I haven't mentioned a sensitivity study. Sensitivity study is a study that allows you to go in and basically inquire how, what's the word I want? How important a dimension or a parameter is to your analysis model. So let's take the diving board. Everybody's seen a diving board, and we got the deflection on the end where you're bouncing to get ready to go into the water. If I change the width of that diving board from, let's say, 24 inches to 25 inches, that's going to have a minimal effect on the deflection of the diving board. It'll have a little, but not a lot, because we still have our same cross-sectional dimension depth, although it is a little bit wider. But if I change the thickness of that diving board by 1 inch, so I change it from 2 inches thick to 1 inch thick, that's going to have a drastic effect on the deflection of the diving board. So we can use sensitivity studies to go in and determine which dimensions or parameters are important in the analysis. And then when we run our optimization study, we only include the dimensions that are going to be important to our study. There's no need for me to put in the width of the diving board if it has infinitesimal or minimal effect on the deflection of my diving board. That's just more parameters, more meshing, more runtime, more computer time. It just takes longer. If it has minimal or no effect, then there's no need for us to include it in the optimization study. Where's that determination made? It's made by the user. If you think it's important, by all means include it. But that's why we have our sensitivity studies that will let you go in and use that to determine what values are important to the simulation that you're wanting to run or you're trying to run. So we have seamless integration with other modules within Creo. If you happen to own a Creo software package, then what you can do is you can do, I'm going to say MDO. These are other analysis functionalities that we have out there. MDO is mechanism design optimization. It actually calculates the forces that you would get from an object moving. So a shock absorber has dampening to it. A spring has a spring force to it. So we can use the MDO package to determine what those values are. We can transfer those directly into a simulate model. You do not have to redo those. You can go into BMX, which is called behavioral modeling. That will let you go in and do optimizations. You can specify goals to set. You can look for a maximum strength. You can look for a minimum weight. You can look for maximum volume. And you can take those values and again, port those directly into your simulate process so that you don't have to again go back and redo them. PTC now comes with MathCAD. All PTC licenses have a MathCAD Express built into it. And so you can go in and you can use your MathCAD. You can use those design engineering calculations, and you can use those calculations to update your model. So once you have numbers from Simulate, you can tie those into MathCAD, and then you can have MathCAD drive your model. A little bit about accuracy and reliability. The P-element technology for meshing is what is used within Creo. The H-element method is used in a lot of the other ANSYS, McNeil-Schindler types of analysis packages out there. It's just a different process. One is just as valid as the other. Some people prefer one, some people prefer the other. The H element, just so you know what it is you have your meshed element, and if you need to refine your mesh, it in essence cuts that edge into half, and you now have 2 elements or 4 elements or 8 elements, and you still have a linear equation between those 2 points. What the P element or polynomial element technology does, and we have auto meshing within Simulate, is you don't need to worry about your element types. It will automatically pick the best type for your model. It will automatically generate the mesh for that model, and I'll show you here in a little bit what it looks like. And then you can actually capture the geometry contours with the mesh that you get. Now, you can change the mesh by changing the parameters that are set up. What's a minimum edge, a maximum edge, a minimum angle, a maximum angle. Or you can do what's called seeding the mesh. If it finds a point or a line or an edge or a surface, it stops. So if I've got one big surface, this 2 by 2, it could be one element. I put some points on the edges. Each one of those points is going to be the end point of an element. So I can increase my element count by doing what's called seeding the mesh. That's all done automatically within the system. And you have automatic convergence. There's 2 convergence methods within Simulate, and I'll mention them briefly when I do a static analysis here in just a few moments. You have a single pass adaptive. What it does is this is the polynomial order or the edge to an element order of 3, runs the analysis, runs through an algorithm, predicts what the polynomial order of each one of the edges should be, sets it to that, reruns the analysis. That gives you an automatic convergence. Now, I know that sounds kind of like foo-foo dust and magic, but as you start using this, you can prove it to yourself. You can run a single pass adaptive, and then you can turn around, run exactly the same analysis with exactly the same setup as a multi-pass adaptive, and you will get similar results. You will not get identical results because you're never going to get an identical perfect result. The models are perfect, the numbers you put in are perfect, but when you test these in the real world, nobody can make every single thing perfect. There's always variation. That's why we have tolerances. So let's talk a little bit about the packages that you have out there for the Simulate package itself. One that's not listed here, that's included with the actual Creo Simulate package, is called Creo Simulate Lite. What it does is it has a wizard that will walk you through it. It says, specify your material. You do that, it checks it off, and then it tells you, go specify a constraint. You do that. Once you have successfully done that, it will say, okay, that mark's checked off, go add a load. Specify a type of analysis. It will not let you proceed until you have done it correctly. It is a light package. It is in every package of Creo Simulate out there. You must install Simulate when you're installing your software to get it. If you do not, you'll have to reinstall. You cannot reconfigure and get it. It has to be installed from the beginning. All packages of Creo Design Essentials, which is considered a T1 package, and all packages above it, T2 through T5, have in them Creo Simulation Elite. That's the one that's listed right here. It gives you parts and assembly analysis, static structural analysis, the element modeling idealizations, auto meshing, and results and reporting. That comes in every single Creo package out there. You do not have to purchase simulation. Then there's the Creo Simulation package, which is out there, which comes in, and this is where you start going into the creating and tweaking the mesh. You get modal analysis, you get buckling analysis, you get steady state, the basic thermal analysis package. It lets you do optimization, it lets you do contact, and it lets you do something called mid-surface compression. What that does is take very thin objects like sheet metal parts or something whose thickness is very thin compared to its other 2 dimensions, lets you compress it to a surface, and then the thickness of that object will become a parameter, not an actual dimension. So that's just a way to tweak or create an idealization in order to get your analysis to run faster. This is the Creo Simulation extension that is a purchased add-on. The other add-on extension is the Creo Advanced Simulation extension, which adds large deformation, and then it adds all of your nonlinear contact, nonlinear materials, your pre-stressed static and modal, your transient or time-dependent structural, your transient or time-dependent thermal, and then your vibration and your dynamic analysis, which is your dynamic shock, your dynamic frequency, your dynamic time. And then this one, combined structure thermal. As you heat up an object, it builds up internal stresses. Those stresses can then be taken into account and brought into a structural analysis. So you have the physical loading that you're going to get by applying a force to something, plus you have the internal loading or the stresses that are built up by heating up an object. That's called a MEC-T, or sometimes you may see an M with a T beside of it if you're in the simulation package. That's called a combined MEC-T analysis. Capabilities. Your capability for your elite package, this just goes through it in detail as to what you can do. So the user has a user interface, linear static analysis. It simulates parts and assemblies. You can do forces, moments, pressures, bearings, temp, gravity, support constraint types, displacement, planar ball, and the like. I'm not going to go through all of them. Materials, it only does isotropic linear materials. That's for the elite, okay? Your Essentials Premium, your Design Advanced, and your Design Advanced Plus all give you the ability to do different things. It lets you do contact interfaces. So a license check system will notify the user if you try to do something that is not supported. So it will let you set it up or try to set it up, but it will give you a warning that says you don't have this particular license. It may be you own it, someone else is using it, or it may be that you just don't have it and you need to talk with sales and get someone to get it into play for you. Business value, lower life cycle cost. You can build multitudes of models in the computer system digitally and drastically reduce the cost that it takes to go in and redo, repair, or redesign a model from scratch. You can reduce your time to market. Again, it's reducing the cost. You can reduce your time to market because if you're building an engine or you're building an airplane or you're building a car, that takes time. You can do that in the computer digitally much faster, much easier than you can in your workshop or your machine shop. You can design toward a price premium. You can set up and do comparative examples between different price breaks, different price materials. I can set it up and say it takes 3 pounds of steel to do this. If I want to do this in aluminum, it may take 5 pounds of aluminum because I may have to change my design to make it stronger because aluminum in certain cases isn't as strong as steel. You can increase your quality and performance because you have a driven design optimization. You know what you want it to do. You can try various different what if scenarios. You can optimize for maximum deflection, minimum weight, maximum volume, whatever you decide to optimize toward. And then obviously you're going to reduce your product development cost because you're not buying 5 cars, 5 airplanes, 5 of whatever, 10 of whatever. You're not having to spend all that money on the physical objects. You're working with the digital objects. Some success stories. Okay, so we have IMSE used Creo to cut months off of prototype development. Boston Engineering, turnkey electrical mechanical software. They reduced time to run simulation by 60%. Kind of know about those a little bit. Great Plains Manufacturing. Great Plains is a huge customer for PDSVISION. I've talked to them quite a bit. Our head of our application engineers has done lots of work with Great Plains Manufacturing. They have a 3 times improvement in time to market and a 40% lighter product. So these are customer success stories that have been provided by the customers to PTC and to us for us to go out and put out there So here's one, a British auto racing team, Aston Martin. We're all familiar with the Aston Martin, the James Bond car. Use Creo Simulate to understand the impact of the model as it would be moving through. So I've taken about 45 minutes of my hour, and I've talked quite a bit. I want to show you the interface, show you what we can do with Creo. This is a part, this is a bracket that would go onto a shelf in Costco or Sam's Club or something, and we've got a rod that would go through here and hold it up. This was designed in Creo. Basically, I created a sketch, extruded it symmetrically about the center axis plane, and I put a hole in it. So thank you, Michael. Okay, thank you. Thank you very much. So I'll go back. I created a section. This is nothing more than a bracket that goes on a shelving system, like I said, within Walmart, Sam's Club, Costco. So I created a sketch. I extruded that sketch in two directions symmetrically about a datum plane, and I put a hole in it. So I'm already in Simulate. Let me show you how to get into it. Here's the Creo interface. So if you're familiar with the Creo interface, then this is what it looks like. Applications, Simulate will throw me into Simulate. I have all of my icons. So I'm in structure, thermal. I can regenerate my model. Here's where I add my loads. Here's where I add my constraints. Here's where I add my materials. And we'll talk about each of those here in just a second. So here's my model. And so I want to go in and I will show you what these are. First off, I have a material assignment. So we'll just edit the definition of that material assignment. This little box is going to pop up and I'm going to say more. We have legacy materials. These are the old Rasna Mechanica materials, and you can use those. We have fluid materials. We're not doing fluids for this. We're not doing flow. We don't need those. We have composite materials. PTC has a product called Composite out now where you have different plies of materials, so you can use composites. And then we have our standard materials database, which allows you to pick ferocious, non-ferocious materials. Yes, I did that on purpose. Plastics, woods. So we can go in and pick any of those materials. So I'm just going to go back into legacy. We have steel specified. It's already in there. So if I select on this, there's the properties of steel. Now I'm going to hit cancel. Yes, I want to cancel. I can go in here and I can create a new material. This is a new solid material. Give it a name. What is this symmetry? Is it isometric? Is it orthotropic? Is it transverse orthotropic? And you would know these things if you're creating your materials. What's this Poisson's ratio, Young's modulus? What's this material limits? If you're doing any type of advanced failure analysis or fatigue, you would be entering your failure criteria. So you would just populate that infrastructure. Specific heat, thermal conductivity for thermal. Composite materials, if you're creating a composite. Miscellaneous information, Y factor, bin tables, so sheet metal properties. Appearance, you might have a specific color. You want to define something specific about it. One thing that I would say when you're creating a new material is where it says description, add a note. Tell me or whoever's looking at this where you're getting these numbers. Because if we run an analysis and it doesn't come back right and we have to troubleshoot it, one of the things we'll have to check is your material properties. Are they accurate? Well, maybe this number here is supposed to be 0.27, and you do like I do on occasion. You have a fat finger and you type in 0.72. Trust me, a Poisson's ratio off by that much will make a large difference. But I can't validate that Poisson's ratio if I don't know where the value comes from. So that's how we can create our own materials. I already have a material set up here. Close this. So I already have a material set up here and it gives me this number in material assignment. Excuse me. I don't have any loads and constraints because I was going to do that. I'm going to come in here and I'm going to say I want to apply a constraint. And I want to come over here and I want to take that surface, I'm going to lock that surface. It's not going to move in the X, the Y, or the Z. So now that's locked down. I have a model, I have my material, I have my constraints. Let's go and apply a load. I want to do a bearing load. I'm going to pick this surface, and I can do a component, or I can do direction and magnitude, or I can do a directional point. So I'm just, whoops, wrong one. I want to do directional bank. So I want to go in the Y direction -1, and I want to give it a magnitude of 250, and we'll just say newtons. Preview. Always hit the preview button. Notice this is going straight down, but it's a bearing load. It reduces itself as it goes around the bearing. I always hit preview. That way I've got an idea of what my load is going to do before I ever run my analysis. One mouse click and it gives you all kinds of information. So I say, okay, now I have my loads there. I want to run an analysis. So I can come up here. I have an analysis there. So I can go File, New Analysis, and specify what I want that to be. So in this case, I can say new static, new modal, new buckling, fatigue, pre-stress, dynamic. Here's my design study. This is my design of experiments, what if. Here's my sensitivity study that's going to tell me whether or not I have a need to include that in an optimization. And then here's an optimization study that I can run. Hey, guess what? Michael, that I was just speaking to, Michael runs a study and he wants me to check it. All he needs to do is send me the study because it already has all the geometry and everything in it. I can import his study and then I can go and work on it just like it was mine. We don't have to worry about any data like that. So I'm going to go in here and I'm going to tell it to start this study. I'm going to overwrite the one that's there. Yes, I want error detection. And notice that happened fairly quickly. Now, I've got an analysis machine. It happens fairly quickly. It'll take a little bit of time, but I can go into the, hopefully you can see it now. So I'm going to do File, New Static. I'm going to accept everything. Say OK. So now I'm going to run that analysis. I've gone about as far as I can go. Good, thank you, Militia. I've gone about as far as I can go. We've shown you all of the different options you have within the Simulate realm. I've only just graced the surface here with what we can do with this simple static analysis. It's very simple and very straightforward to set up. It's very simple to run and analyze the data. This is telling me I have a von Mises stress of 1.64 megapascals. That may or may not be an accurate number because I just threw numbers on it. I didn't apply any engineering knowledge to it. I just threw a number out there. But that's how easy and simple it is to set up. Militia, I'm not going to change my screen because I don't want to do anything. Are there any questions that came in on the chat that you can relay to me before we call it a day?
No questions just yet. Maybe there's more questions. Let's allow a minute or so, and then I can just tell you if there's any questions incoming.
Thank you. And if anyone on, excuse me, anyone on the presentation, if you have questions, feel free to reach out to myself or Militia. She'll get them to me. I will get the question answered for you and get it back to you as soon as I possibly can. So, and that's usually within a half a day to a day. I don't like to let questions sit around. I know you ask them for a reason, so you need an answer as soon as I can. If anyone has any questions or any comments or anything, I appreciate your time that you took to sit here and watch this and listen to me. I hope I didn't bore you. I hope I didn't put you to sleep. So thank you for attending. Be on the lookout for one on Creo ANSYS. That one will be done by Sevi. I won't be doing that one. Sevi will be doing that one. Don't know the date of that one yet. It's still to be determined, but that'll be the third of the 4 series that we have. So thank you everybody for joining. Yes, go ahead, Militia.
Sorry, Terry. The Creo Answers webinar is actually set for September 4th.
Okay, thank you. I was not aware that a date had been set yet. So mark that on your calendar, September 4th. And I'm sure that hopefully you'll enjoy that one as much as you enjoyed this one, or I hope you enjoyed this one. I have nothing else. I will turn it back over to Melissa in case she needs to do anything. Again, thank you for joining. And if I can be of any help in any way, Creo, Simulate, anything, feel free to reach out and let me know.